Alright, so using this idea of binding energy and this idea of when particles come together they bind and they form energy. I'm talking about a deuterium. If you hear the word deuterium, this is what we're talking about. It turns out to be a hydrogen particle. Hydrogen, which is pretty cool because they've actually talked about using this as a possible power source. So deuterium is relatively common when it comes to radioactive material, unlike uranium. So when you talk about that, you need to understand a few things. So deuterium is one proton and one neutron. That's why it's a hydrogen. Hydrogen is one proton. So you've got the one proton, one electron, but also bonded to that proton in the nucleus is this neutron, which makes it a heavier particle. So hydrogen being approximate is 1. This right here turns out to be 2-ish. The actual mass value for atomic or a unified mass unit is a 2.014102. You can see that in the video, so we're just going to leave it as that. But remember, when we came up with the unified mass unit, we determined that the mass of a proton is equal to this, the mass of the neutron is equal to this. Okay, so these are the values for a proton and a neutron. So if I add them together, I get this numerical value, 2.01649. So a proton plus a neutron, any situation, should have a mass value of this. But this deuterium has a mass value of this. So there's a difference in between them. Well, that's alright, because what we're going to do is we're going to look for this mass defect. This delta here, this lowercase delta, is referring to the mass defect, the difference in the masses. So I take these two values together, the mass of the proton and the mass of the neutron, which is the total mass value that I should have. Okay, the total mass value that I should have. Okay, if I counted the number of protons and the number of neutrons, I take the number of protons and multiply it by the amount of mass per proton. I take the amount of per neutron. So number of protons times the mass per proton plus the mass of the neutron, or the number of neutrons, times the mass of those neutrons. So the number of neutrons times the mass per neutron. So I've got the number of protons times the mass per proton, the number of neutrons times the mass per neutron, gives me the theoretical mass value, the mass value it should have, okay, if matter was conserved. And we know it's not. That should have. This right here is referring to the amount of mass that it should have minus the amount of mass that it does have. So this is the amount of mass that it does have, this is the amount of mass that it should have, and you get a mass defect, the missing mass of this. Okay? So this right here is referring to the mass defect, the amount of mass that it is missing. Okay? This is what it should have, this is what it does have, this is what it's missing. Okay, all of that matter has been converted into energy, into binding energy that binds my protons and my neutrons together. Proton and a neutron, because that's all we have. So using this E equals mc squared idea, that energy is equal to m, mass, in this case mass defect, the amount of matter that is missing, times c squared, and I've converted c squared in here to mega electron volts. So just to give it to you, so c squared, which is the speed of light, in mega electron volts per unit, atomic mass unit, is 931.494 mega electron volts per atomic mass unit. Okay, so you might want to write that number down. I don't know how common that is on a test. If I figure that out, I get the binding energy that's between this proton and neutron is 2.224 mega electron volts. That's how much energy. That's how much energy is in the bind in the bind between this neutron and the proton, not per particle. I caught myself on there. It's in the bind in that neutron and proton. Now, if there were more, and this is what I would get, this is the total amount of binding energy. This is the total amount of binding energy. If I wanted to calculate the amount of binding energy per particle, I can take that number and divide it by the number of particles. Okay, so a proton-neutron, I would divide this by 2 atomic mass units. I have 2 of them. So that would tell me the amount of binding energy per particle. Cool? Does that make sense? So this gives me the idea of how much binding energy there is. Okay, if I divide it by the number of particles, I would get the amount of binding energy per particle, which is actually an important piece of information.